Hi, I'm Joyce. I'm on behalf of Princeton Satellite Systems. I'm presenting our work on space rapid transit, a horizontal, reusable, two-stage to orbit launch vehicle. So first, let's talk a little bit more about the history and developments of horizontal takeoff. Why do we care about horizontal takeoff when we already have existing rockets that use vertical launch? So this has actually been conceptualized since the 1950s under the idea of a mobile launch pad. The idea is essentially we want to be able to use standard airports, or in this case for SRT we found, but space rapid transit we found that we have a roughly 2.27 kilometer airway. You could actually launch the whole system. This is actually a picture I took earlier in the flight when landing alone. So the idea is that we'd be able to enable more countries to have a launch facility of their own, assuming that they have an airport or airway that could be used already. So there are two main concepts that we can play with: a single stage to orbit using a hypersonic space plane. This is simplest from a concept of operations perspective, but it requires the entire launch concept to reach LEO, so more mass to lift. An example of something that used this concept was the Rotorverse space plane. The other one is this two-stage to orbit concept, which only requires the second stage in the payload to reach LEO. An example of this is Germany's MPV's Stinger 2. And this is similar to what we are proposing for space rapid transit, which is a conceptual two-stage to orbit launch system that has actually been published about by Princeton Satellite Systems since 2010. So you can always go look back in both papers too. But for this innovation, in terms of updates on the design for space rapid transit, we're examining a 500 kilogram payload to low orbit compared to Stinger 2, which had a roughly 10,000 kilogram payload to low orbit. So our overall launch system is much smaller than Stinger 2, which would make for an overall smaller and less mass for the whole system. So hopefully cheaper to develop as well. And we talk a little bit about that in a minute. In terms of the first stage, this two-stage to orbit, it uses a hypersonic glider, which we call a ferry, which is powered to the propulsion system by a hydrogen-fueled ramjet and two patented F-135 turbofans using standard hydrocarbon jet propellant. The second stage, which we call the orbiter, is a rocket booster using the LRL-10, which is already a TRL-9 engine by a jet rocket. So for the overall presentation, I'm going to talk a bit about the concept operations and also talk about the overall trajectory of the flight path to 350 kilometers, or ISS altitudes. And then based on what we find from that, we propose some initial inlets which would meet the conditions for the separation altitude and Mach number required for the separation and what's required for the ramjet operation. And I'll also talk a bit about future development in the business model, like why would we even want to develop a two-stage to orbit hypersonic launch vehicle. So from a concept of operations perspective, we start with a horizontal takeoff just using the turbofans, and then the turbofans accelerate to Mach 1.5, and at that point, then the ferry engines would switch to the ramjet. So the turbofans shut off, then the ramjet is in operation for a hypersonic sprint to Mach 5. Then the RL-10 ignites for the orbiter to separate from the ferry, following a coast burn into 350 kilometer orbit. And all the while, the ferry returns for power landing horizontally back into airways, and the orbiter also returns down. From a GNC perspective, this was actually published about several times in previous papers. Essentially, for the overall software architecture, both the ferry and orbiter are unmanned and autonomous. They have basically independent architecture, but it's pretty similar. There's just a few differences in the sense that for the ferry, there's some additional actuation interfaces just for the turbofans, mating, and ramjet. Alright, and now look at the trajectory. So using basic equations from the GNC and also some additional equations for the point mass aircraft, as well as the equations for the orbiter. We want to achieve an objective of switching between the turbofans and the ramjet at Mach 1.5. And we also want to achieve separation around 40 kilometer altitude, like the Stinger 2. So essentially within this trajectory, we examine this within three main phases. One just using the turbofans, then the ramjet, and then a third larger segment looking at the RL-10 using similar methods, same methods from the previous papers, which were presented at the International Congress, Aeronautical Congress in HISST last year. Essentially from this we see that we're able to achieve roughly 39 kilometer altitude for the separation staging, and in terms of the Mach number, the ramjet only needs to go up to 5.3. In the overall initial stage, we have the limit for the ramjet going to Mach 6, since that's one of the upper limits. But in this case, we actually find that we don't need to go all the way to Mach 6. We can achieve what we want for the separation around Mach 5.3, which then makes for a slightly easier inlet design problem. I'll go into that. Still not the easiest. In terms of the overall profile of the fairing orbiter, this is what we obtained from the trajectory analysis. Again, as I pointed out before, separation occurring at around 39 kilometer altitude, lining up to Senga 2 analysis, and the fuel being roughly 18,000 kilogram for the orbiter and roughly 2,685 kilogram for the fairing. So now I'm talking about the inlet design. So we want to achieve compression of incoming air for the conditions required of the combustor or the engine face. And we also want to balance between trade-offs between the pressure recovery and the overall inlet mass. And in general, one reason why we care about the total pressure, so in general we can assume that for 1% loss in total pressure, it's also been found to correlate with 1.5 loss in engine thrust. So we do want to try to find a balance between these different parameters. In terms of the propulsion system for the Pratt & Whitney, and for the overall inlet design, I used NASA's Supersonic Inlet Design Analysis tool, which is essentially a computational tool which generates geometry files, performs analysis of mass flow rates, pressure recovery average along different cross-sections of the inlet, assuming quasi-one-dimensional flow or planar model, depending on which version of the inlet you're looking at, adiabatic flow and ideal gas. So for the Pratt & Whitney turbofans, I followed a similar external compression inlet as what was already in the sample files of Superman. And we were proposing just ramp doors to switch between the turbofans and ramjet. And between both designs for the ramjet and turbofans, there are the standard equations for the mass flow rates along the inlet, flow function based on the specific heat ratio and Mach number, and also the ideal gas law, as I mentioned before, as one of the assumptions. So the harder inlet design is for the ramjet because it requires a larger compression difference between going from Mach 5.3, and we also wanted to go to subsonic conditions for the combustor. So in this case, I'm assuming Mach number of combustor of Mach 0.38. With this three-stage ramp with an isotropic second stage, and starting with the conditions of 40 kilometer, 3 degrees equal attack. Also assuming a rectangular engine face, so a rectangular ramjet with the dimensions as displayed. And in this case, as I mentioned before, it's an external compression inlet with a diffusing isolator. Essentially, we played around with different sizes for the ramjet. And found that with the pressure recovery, depending on what Mach number we choose for the CAL, for the start of the CAL interface, that's what determined how long the Supin would design the overall diffuser to be. So in my case, I was trying to overall reduce the mass, so the pressure recovery is a bit lower. However, for next step, we're also examining different geometry. So for the hotel, as mentioned before, it was a single stage to orbit launch vehicle. That one also faced similar issues with the inlet in terms of the balance between pressure recovery and the overall mass. So in their case, they ended up designing an inlet for around Mach 4 using vertical wedge intakes. So that's another geometry that we're also considering for the inlets for the ramjet. So for continued development for space rapid transit, the ramjet ferry and orbiter can be jointly developed. So right now, we're still doing high fidelity simulations of the overall trajectory. Also want to look at the entry and separation conditions in more detail. We also want to do high fidelity computational fluid dynamics to actually validate some of the numbers generated by Supin, although Supin numbers in general do line up with some of the CFD numbers I've seen reported that also use Supin, but there's still, it's averaged along cross-sectional areas along the inlet. So it's not perfect, and a computational fluid dynamics software that can actually look at the inlet as well would be helpful for validating conditions. Essentially, jointly, the ramjet ferry and orbiter can be kind of separately tested to bring each component to TRL9 until the other components are ready for a combined flight test. So for the business model, according to NASA's Advanced Missions Cost Model, which just provides a preliminary cost model for estimating how much it may cost to develop a full launch system based on the dry mass, we estimate that it could range between 7 to 13 million USD, depending on the difficulty of developing SRT. And as a visible system, we also want to think about the refurbishment cost. So I looked at the X-15 US Hypersonic program to see how much their refurbishment costs between different X-15 flights. And the numbers from like 1960s were around 300,000 USD between different launches, which ended up being roughly 3% of the total program cost. So in that case, we're also going to assume somewhat similar numbers in this case. But in terms of why we want to even develop space rapid transit is that it is able to enable terrestrial tempo from multiple industries within low Earth orbit commerce. So this more broadly includes transportation and logistics and on-demand launches. But in particular, we do want to point out that there is important pharmaceutical, biology, and semiconductor research currently happening at the International Space Station. So if we have a launch system which can launch more frequently and actually be launched on demand whenever a pharmaceutical company wants a product to be delivered, or when they want supplies to be brought up to the ISS, this system would essentially enable that type of technology, as well as precise insertion of small spacecraft. So that right there is actually a conceptual space station designed by Michael Pawluszek, who's also one of the co-authors of this paper. In conclusion, space rapid transit, overall these updates are designed with the idea that the turbofans right now are already in use. So we're trying to get the components that are already separately at TRL9 while bringing up these other components to a higher design level. That way we could try to increase the speed of development for space rapid transit, although it may still take 5 to 10 years. But overall, this design presents updated sizes for the 500 kilogram payload, updated trajectory flight analysis for reaching 350 kilometer altitudes, inlet design, the initial inlet design to meet the objectives from the combustion. I also examined different tank geometry for the liquid hydrogen storage as well. But as I mentioned before, one of the next steps is further examining the inlet and looking at different geometries. I also want to give some quick acknowledgements to my colleagues, Chris, Sarah, Layla. Sarah's at MIT right now. Also, John Slater, he's the creator of Supin. He's been willing to meet me on Zoom quite many times just for us to bounce ideas for inlet design. I don't have to speak